Hello, everyone, and welcome to today's exciting webinar. I am Tim Stark, and the host of today's exciting event. I am a professor of civil engineering at the University of Illinois at Urbana-Champaign and technical director of the Fabricated Geomembrane Institute. This is our 7th webinar of 2020, and the remaining 10 webinars for 2020 have already been scheduled with great speakers and timely topics, which I will show you on the last slide today. We're having a webinar every 3 weeks now instead of every 4 weeks, so we hope you can still join us. During today's webinar, we welcome questions and comments which can be typed into the questions box in the control panel. You may send in your questions at any time during the presentation, and our speaker will address them at the end of today's presentation. The recording of this webinar and a PDF of the slides will be made available on the FGI website after today's presentation. PDH certificates will be sent automatically to all who attend the entire webinar. Today's webinar speaker is Mr. Eric Blond. Eric is a consultant offering technical services in the geosynthetics and engineered construction material industries for the last 2 years. His key areas of expertise are soil filtration and drainage by geosynthetics, durability of geosynthetics and construction materials, geosynthetics lining systems and materials, and other applications of geosynthetics. Prior to starting his consulting firm, he worked with Sageos for about 23 years, so he has considerable hands-on experience with testing, specifications, and design of drainage composite. He has also been actively involved in several standardizations committees, such as chairing the ASTM subcommittee D3502 on geosynthetics durability, chairing the Canadian Mirror Committee of ISO TC21, and has served as the task group leader for the development of several ISO test methods on flow capacity of drainage composites and ISO 18228-3 on designing geotextiles for filtration. The title of Eric's webinar today is Testing and Design of Drainage Geocomposites, which is a topic that has been requested by a number of our prior viewers. Eric, thank you for squeezing this webinar into your busy schedule and joining us from Montreal, Quebec. The webinar controls are all yours.
Thank you, Tim. So you hear me? Everything is working well?
Yes.
Okay. So good morning, everybody. Good morning, good afternoon for those of you who are in Europe. So today, as Tim introduced, I'm going to present to you what I know about testing and design of drainage geocomposites. So first thing first, why do we need to do so much some testing on the geocomposite? If this wants to move, oh, okay, maybe here. Okay, so first, what I'm going to discuss. I'm first going to present the structure of a drainage geocomposite. So there are different products on the market. Each of them have its own features, properties. And how can we compare them on an equal basis? How can we compare the long-term flow that we can develop out of a geocomposite, disregarding the details of the structure? But for that, we need to know what are the specifics of the structure and how they behave. Then I'm going to briefly present the design objectives. When we design a product for drainage, what do we want to achieve? Then we'll go into determination of the short-term flow capacity, what is seen on the specification sheets that you get from manufacturers, from suppliers. After that, we have the next concern is how to assess the long-term performance. So, of course, the products change over time. There are different degradation possibilities that can happen, and all of them are taken into account by the various design methods. Then I'm going to make a quick remark on the other design concerns, which I'm not addressing today. And finally, we have a concluding remark. And of course, the very what I'm looking forward to interact with you with questions and answers. So first thing first, what is a drainage geocomposite? What are we talking about today? First, it's a drainage core. It's composed of two key components. A drainage core, which is the component which is designed to convey the water from A to B. Second, there is a geotextile filter, which separates the soil, which is next to the geocomposites, from the core. So it avoids the soil particles to enter the core. It acts as a filter to preserve the integrity of the core on the long run. And the combination of both these components creates the drainage geocomposites. There are several cores available on the market. The most common, this beautiful drawing you see on top left, I have better photos after, shows a GeoNet core. So it's a set of ribs which are intersecting and creating some kind of spacer which offers a volume for water to flow. Then you have webs or mats, geomats, which are random fibers organized in different directions, in random directions. So the intention is always the same: maintain a thickness, a void, an air gap, a void through which the water can flow. You have double cuspated or single cuspated sheets. These are very common in the building industry. It's actually the standard product for drainage of foundation in the building industry. And they have to be designed just the same as any other product. You have three-dimensional boxes, geocomposites as well. So the GeoNet is composed of some kind of boxes. You have multilinear drainage geocomposites, which are small pipes which are confined between two geotextiles. So in that case, it's really a different type of product. Instead of having the entire surface covered by a drainage material, you have pipes with a higher flow capacity for each line, which are capturing the flow and conveying elsewhere. And finally, you have structured geomembranes. There is so the geomembrane itself, that's for use in very specific application where you do have a geomembrane installed. So the geomembrane is developed with a structure that makes a spacer when in contact with a geotextile or another geomembrane. So that's the 6 different type of products that we can see regularly in our industry. So when we want to do some drainage, what are we trying to achieve? We want to, for a geocomposite to work well, we want to maintain the water head within the thickness of the drainage geocomposites. So the first thing that we need to know is how much water we're going to have reaching this product. So this is controlled essentially by the rain intensity. So there are tables, building codes for every region provide some data on the intensity of rainfall with occurrence of 20 years, 100 years, I don't know what. Other aspects which are going to control the flow is the angle of the slope. So typically we consider that the gradient of water is equal to the angle of the slope. So a vertical product, like if you are installing a product on a building, on the wall, outside of wall of a building, the gradient is 1. So the direction of flow is vertical. The length of flow is equal to the water head between for the length of flow, so the gradient is 1. If you have a slope of a 2% slope, so that means you have 2 meters difference of height over 100 meters length, this is a gradient of 0.02. The length of the slope, of course, is going to control the design, because the more you go into the slope, the more you go into the product, the more water is accumulated coming from elsewhere. So the length of the slope cannot be infinite. It has to be, it is defined by the flow capacity actually. And all of that leads to a maximum flow capacity, which has to be put in relation with these other parameters. So when we do the design of a drainage geocomposite, what we must make sure is that the geocomposite never reaches saturation on a slope for a gravity drainage. The reason for that is that if you reach saturation in the geocomposite, then that means, obviously, that the water starts to flow in the direction of the slope within the soil veneer. on the slope. And that means you start to have instability developing in the soil. You start to have pore pressure building up. Up to some point, you're going to have, you can have actually a water pressure pushing up the soil, and creating a problem that we don't want to have. And that can lead to that kind of situation. So on this photo, actually, I think this photo had no drainage at all, which is what was even worse. But the seepage of water into the soil veneer eventually led to the soil being completely evacuated from the slope. So that's exactly what we don't want to see. So overall, when we do the design of a drainage geocomposite, what we want to make sure is that the flow capacity of the geocomposite will exceed the expected flow of water reaching the geocomposite. And this value is determined by the site, by the environmental condition. You won't have the same factors in arid regions than you have in humid regions. This all relates pretty much to standard geotechnical design. There are some very interesting guidance provided in the new test method ISO 18228-4, which is in press right now. It's been completed about 1 or 2 years ago, but the time needed in the ISO process to publish standard is relatively long, and there is lots of verification and so on. So the document is in press right now and will come out by the end of 2020. And what's really interesting is it's one of the first documents I see in the geoscientific industry which provides relatively good guidance on how to assess the water flow, the flow capacity that must be met by the drainage geocomposites. So geocomposites have been around for some time. There has been some failures, as you've seen on the photo I just shown you. And of course, the industry has taken immediate reaction to develop design guidance. The first one was the Geoscientific Institute, and in 2001, they have published GRI GC8, determination of the allowable flow rate of a drainage geocomposite. This document is widely used. It's actually probably still the most widely used specification for designing geocomposites. It was improved in 2018 by ASTM D7931, which is basically the same GRI document with additions, modification, upgrades, as we will see later. And a similar work was done at the ISO level in Europe. And in 2020, we will have the ISO 18228-4 design of drainage products for geoscientics. All of these design guidance are based on the same strategy. You define a safety factor, which is a ratio between the allowable flow rate provided by the product and the required flow rate, which is driven by the environmental condition. The factor of safety must be greater than 1 always. Otherwise, if it's lower than 1, you're exposed to a failure. So this strategy is really common to all the design methodology which are around. What are the key differences between those methodologies? So essentially, in GRI, the factors that were considered based on what was understood and known at that time, in the late 90s, early 2000s, the reduction factor that had to be considered were essentially creep, chemical clogging, and biological clogging. For different reasons, this situation has been working very well, and I'm not aware of so many failures when the product is well designed per GRI GC8. But still, for different reasons, there was an interest in adding more consideration in the design. One of them was geotextile intrusion, and we will get into that later. And geotextile intrusion was accounted for in ASTM D7931 in 2018. And finally, any test has inherent viability. And in the ISO standard, the proposition which was made by the work group was to also include a reduction factor for laboratory uncertainties. that should be taken in consideration while designing a system. So at the end, what we need to do to design a drainage geocomposite, we need to know what is the required flow capacity, which is determined by the site environmental condition. We need to know the short-term flow capacity or transmissivity, which is product-specific, determined using different test methods. And that's what we're going to discuss next. And we need to define what are the reduction factors that must be applied to define the safety factor for this particular design. So first thing first, short-term transmissivity. There is basically two test methods which are used in the industry for designing drainage geocomposites, which are ASTM D4716, which is really focused on the transmissivity. So the transmissivity is a factor that I'm going to present in the next slide. And we have the ISO 12958, which is the test method for water flow capacity. In the ISO world, they don't like the concept of transmissivity for good reasons, I think. So they prefer to analyze directly the flow capacity. So they don't want to integrate the gradient in the calculation. They want to go directly to the flow. So ASTM D4716 was indeed developed considering that the flow within a drainage geocomposite follows Darcy's law, which means there is a constant relation between the flow and the hydraulic gradient. And so the test method defines the transmissivity as the relation between the flow and the gradient. So the way the test is done, which is the same for ISO and ASTM, is that we have a specimen with a given length and given width, and we apply a hydraulic gradient between upstream and downstream of the specimen. So we control the waterhead, we measure the flow through the specimen, and eventually we can calculate the transmissivity, which is the flow divided by the width divided by the hydraulic gradient under a set of given conditions, which is the normal load, the boundary condition, and the sitting time. So this is a general concept for determination of the short-term properties ASTM 4716 or ISO 12958. Now, I was telling you that people in the ISO world prefer to use directly the flow capacity instead of the transmissivity. The reason for that is that Darcy's law does not apply to the flow in drainage geocomposites. So you see in this little cartoon here, the blue line shows what we know for soils. For soils, there is a hydraulic gradient and there is a flow which is going to be directly related to the hydraulic gradient and the surface and so on. For geocomposites, what has been proven actually in the late 80s and 90s by my friend Piotr Remoldi, I think, if I'm correct, he has identified that there is a relation which connects the square root of the gradient with the flow. So in other words, the higher the gradient, the lower the transmissivity. It doesn't mean that the flow is lower. It means the transmissivity, the parameter calculated with the test is lower. So if you look at the transmissivity, of course, the flow continues to increase, but the transmissivity decreases. So, and this can be an order of magnitude of difference. If you look on the right-hand side, you have in a linear scale, you see a relation, which is a true relation between the gradient and the transmissivity. So for very low gradient, you can have a transmissivity which is one order of magnitude higher than for high gradients, like 1. What I'm using very often as a rule of thumb, which is consistent with the equation you see there, is that every time you have an increase of hydraulic gradient of 2 orders of magnitude, you have a decrease of transmissivity of 1 order of magnitude. In other words, when you have a 2 orders of magnitude increase of hydraulic gradient, you have only 1 order of magnitude increase of flow rate. So now influence of the normal load. So by the way, you can see here on the right-hand side, the relation between the gradient and the flow, which is always increasing. The higher the gradient, the higher the water flow. For normal load, when you increase the normal load, you have a polymeric product, which is there, a plastic core, and the plastic core tends to compress, to react to the load, and to reduce the void space available for flow. So when you increase the normal load, you will decrease the transmissivity and decrease the water flow as well. So overall, when you look at the properties of a drainage geocomposite, how is the transmissivity influenced by hydraulic gradient and normal load? The transmissivity will decrease with as the hydraulic gradient increase, and it will decrease as the normal load increase. So all this complexity, it sounds a bit complex, and that's the reason why in the ISO world, I prefer to limit the discussion to the water flow and not include transmissivity in the discussion. So now, influence of the type of core. With all these properties that I'm describing, they are definitely influenced by the type of core. To stick to what is the most common type of product sold on the market, which is a geonet geocomposite, even if we limit to the biplanar geonet geocomposite, you have different type of structure for the biplanar. Some geonets have a relatively high strength, which develop a much better, a very good flow capacity on the short term and under low loads. But when you increase the load, they tend to roll over. So you see this mechanism here. In the initial condition with low loads, you have the angle of the two strands, which is relatively vertical. And when you increase the load, this trend that you can see here may tend to bend. So that is reflected by a compression test, a compressive test. So here you have some graph showing a compressive test. When you increase the compression, when you increase the stress, you tend to have to lose some thickness very quickly. So while some other products which have a more stable structure, like this one, which has a rounded strands, these rounded strands will compress still. So there is still an influence of the load, but this influence is much lower. So you should not consider that it's going to be the same behavior for any product. Some products will lose a lot of flow capacity with increase of normal loads. Some others will not lose so much flow capacity. Example of value that we have developed many years ago. Here you have a triplanar geonet. You have a rounded strand geonet here, and finally you have a standard geonet with relatively standard strands. Several products can have different range of capacity, but here we took 3 products which had relatively similar flow capacity at the under low loads, and we've increased the normal load. And you can see that the difference between the transmissivity at relatively high load, 1200 kPa, the difference is huge. It's 1 order of magnitude. So depending on the structure, you can lose up to 1 order of magnitude. You can have up to 1 order of magnitude difference between the properties of the product. Another factor which is going to affect the flow capacity of drainage geocomposite is the boundary condition and the geotextile intrusion. When you have a product with 2 geotextiles confining the void space and a net in between, if this product is between 2 rigid boundaries, like between 2 geomembranes, for example, or between concrete and another geomembrane, sorry, you will not have any geotextile intrusion. So you will not really lose any flow for geotextile intrusion. But then when you have one side which is soil and the other side which is rigid, you start to have some penetration of the geotextile into the void space. And when you have the 2 sides, of course, you have much more loss of void space and thus flow capacity. So I have another photo if it wants to come. Voila. Here, example of a biplanar geonet under load confined between soils. You see that the soil is basically taking all the void space. So this type of product, if it's tested and specified considering rigid boundaries, the value that you're going to consider in the design has nothing to do with what is going to be actually delivered on site. So that's why the soil intrusion into the void space must be considered as a significant factor reducing the capacity of geocomposites. When you have box-shaped products, they behave completely differently. So a box-shaped product, like you can see actually this photo here in the middle, which describes that type of product. These products will maintain a much higher, are much better at maintaining the void space between the two geotextiles. So these products are much less sensitive to geotextile intrusion than our biplanar geonet, for example. Same for triplanar geonets. Triplanar are behaving pretty much like this one. They're much better at preserving the flow capacity with geotextile intrusion. Okay, so it sounds like we should always use triplanar or box-shaped. Actually, maybe not always. There is one factor that makes biplanar geocomposites better than triplanar geocomposites or box-shaped geocomposites. It is the flow, perpendicular flow. In the biplanar have a better multi-direction flow than triplanar or box-shaped. There was a study made in the early 2000s, and they've measured the flow capacity in the direction of the triplanar or biplanar geocomposite, and they've measured what's left in a perpendicular direction or with a 45 degrees angle. And they found that for a triplanar, they published these numbers, which are specific to a product which was on the market back then, but the concept is correct. They found that if you look at 100% in the direction of flow, in the main direction of flow, you can have as little as 18% remaining in a perpendicular direction. And I think my personal opinion is that this 18% is probably on the high end of what you can actually have left. Now, if you look at the biplanar geocomposite, you can have up to 40% remaining in a perpendicular direction. So this is okay. It can be handled. It all depends on the specifics of the project. The one thing that must be well understood when using triplanar or box-shaped geocomposites is that at the time of installation, another factor that must be very well understood is that the direction of flow of the geocomposite must be exactly the same as the slope. You cannot have a deviation, otherwise you're going to lose some capacity because of the orientation of the product versus the slope. Is it coming? Voilà. Sitting time now. So we went through different geotextile intrusion. Now sitting time. Products are sensitive to creep on the long run. Creep takes place in multiple stages. There is a primary creep that we could actually call sitting time. Then there is a secondary creep over which the product loses some thickness over time because it's a polymer, it's sensitive to creep. And finally, there is a tertiary creep, which comes at the very end where the product collapses completely, may collapse completely. In the geosynthetic industry, there's been quite some discussion about what should be the sitting time and how it should be selected to have a proper evaluation of the product. In Europe, the decision that was taken with the ISO standards is to limit the sitting time to 6 minutes, to a very short time, while in North America, the preference is to go toward longer sitting time, typically 15 minutes or 100 hours. We'll see that later. So it's a question, it's a matter of choice. I have an opinion on that, we'll discuss later, but eventually what we have to remember is that the sitting time will affect the test results. The longer the sitting time, the more chains we can capture primary creep-driven failures, but it does increasing the sitting time for a very long time does not does not prevent from having a creep failure on the long run. It only addresses the primary creep failure. It might be missed if we have a too short-term creep time, sitting time, but we still need to evaluate long-term creep time, sit time. So at the end, for repeatability, for consistency, it's always better to use longer creep time, sitting time, sorry. So for design, when you perform the design of a structure, it's better to specify 100 hours sitting time. We'll see that after. It offers better repeatability, and it completely takes away the primary creep from the equation, which has the highest influence. On the other hand, for quality control, for MQC and construction quality control, requiring 100 hours sitting time is extremely long, can be very expensive, and it can be really complex to manage on a job site. 100 hours is a bit more than 4 days. If you add to that shipping to the testing lab, if you reaction and waiting time, normal waiting time, conditioning, you very easily get to 1 or 2 weeks turnaround time per test. And if you have 10 tests to do, which is maybe not a lot, that means the lab should have 10 different equipment only for your project. It's not going to happen. So 100 hours sitting time for specification, for quality control, it's not realistic. So that's why we have these two different options: long sitting time for design when you plan a project, and short sitting time for MQC and CQC, manufacturing and construction quality control. So at the end, when we want to evaluate short-term properties of geocomposite, we have different factors which can affect the measurement. We have the hydraulic gradient. So again, we have a product which is not following a Darcian flow. So we must perform the test according to the hydraulic gradients that we're going to use. And we cannot compare results developed with two different hydraulic gradients. They do not compare. We have the normal load. So the higher the normal load, the higher compression of the product, and the lower the transmissivity and the flow usually. We have the boundary condition. A product tested between two rigid plates does not deliver the same hydraulic properties than a product tested between soft boundaries or soil. And we have the sitting time. The longer the sitting time, the deeper into primary creep you go, and the lower the transmissivity usually. So each and every type of core filter combination behaves differently. So voilà. So that's really the short-term properties. That's really the main thing that we have to remember. Every test reflects the test condition. Every test result reflects the test conditions that were selected to perform the test. And yeah, I've discussed transmissivity and water flow differences. So I'm going to go just a little bit deeper in the differences between the two test methods, ISO and ASTM D4716. ISO 12958 has experienced significant revisions until 2020. I should have written 2019, because in November 19, we had the plenary meeting in Beijing where it was decided to go for publication of the two test methods. So until 2010, there was only one test method, ISO 12958, which is going to be continued as 12958-1 as of 2020. For this test method, we had it was mandatory to test for 3 normal loads, 20, 100, and 200 kPa. So practically, it was not really possible to test under any other normal load. If you're designing a tailing facility with a 1500 kPa active load, the ISO test method was not offering an option for that. There was two hydraulic gradients, 0.1 and 1, so it's always mandatory. The boundary conditions were mandatory boundary conditions were to use closed cell EPDM foam, so that was to take in consideration the geotextile intrusion into the core. And the sitting time was 360 seconds, which is 6 minutes. So this needed some improvement. The 360 seconds remains in the new test method. I have personally lots of questions for that because I think sometimes the duration of the flow measurement is more than 360 seconds. But that's what the committee has decided, where we stick to these conditions. Another factor which is interesting is which is important to point is the dimension of the box. The ISO 12958 authorizes, and actually many of the testing apparatus which are in Europe are only 200 millimeters wide, not 300 millimeters as we are doing in North America. And this has an impact on the flow measurement. Like if you have a biplanar geonet, and if you have a narrow box, the water will be directed by the ribs to the walls of the box. And when you have a shape factor which is high, when the width is much lower than the length, in that case 1.5 times lower, then it will affect the flow that you will measure. Some publication was made about 5-10 years ago quantifying this, but anyway, that's another discussion. So the ISO 12958 is defined like that. Now there is a new performance test which was introduced with for flow measurements. It's ISO 12958-2, which is going to be introduced in 2020, and this one gives much more possibilities. You can use normal loads according to the project specification. So, like if you need to test at 1500 kPa, 2000 kPa, it's not a problem. You can use any hydraulic gradients needed. And you have a proposition to use of some default hydraulic gradients. Same for boundary condition, and very important, the sitting time, which is increased to up to 100 hours as a default proposition. We keep the same box to perform the test. So now, if we look at ASTM D4716, in general, the test method is very scientific. It's a very open testing strategy which is proposed. It provides a lot of guidance for selection of test conditions with some default test conditions, but you have to read between the lines to understand exactly what is specified there. It is typically used for both performance testing and MQC. So what is specific to D4716 as a comparison with the ISO? The normal load, which are proposed are much higher. It goes up to 1000 kPa, much higher than what is proposed in 12958. Hydraulic gradients, the default propositions go from 0.05 to 1, with typical gradients of 0.1 or 1 used. Boundary conditions are rigid or closed cell EPDM foam, and the default condition is rigid to rigid, with the claim that is going to improve the repeatability of the test, which is correct. And the sitting time is 15 minutes. So you see there are minor differences between the two test methods, ISO and the 4716. Now you have for the performance testing, it's pretty much the same as for ISO. One thing which is a bit different, there are scientific considerations for the sitting time. The current wording in the method is you have to consider compression test data, blah, blah, which nobody does ever. Practically, when it's for design, for performance testing, it's going to be 100 hours. Dimension of the box is 1 foot by 1 foot, as I mentioned before. So if we compare side by side, 12958 with D4716, Overall, the methods are similar. So normal loads, it's a bit lower than 12958 than it is in 4716. Hydraulic gradients, very often we see requests for MQC or CQC with very low gradients. One of the reasons for that is that the lower the gradient, the higher the transmissivity, because of what I explained before, of the calculation trick. So when you publish a value with a very low gradient, you show a value, a transmissivity value, which is higher. So the same product tested at 0.02 will exhibit a transmissivity which can be 2, 3, 4 times higher than at 0.1 gradient. So for commercial reasons, it's very good to use lower hydraulic gradients. Boundary conditions now. ISO for MQC, the test method requires soft, so foam boundaries. Practically, what we see on the market is that people are using rigid boundaries, just the same as ASTM D4760. So it's a ad hoc modification to the test method, which is adopted by the entire industry, and by the way, which was corrected in the 2020 edition of the ISO method. What has not changed is the sitting time. So the ISO method requires a sitting time of 6 minutes, while ASTM is requiring 15 minutes. Practical implication of that is that results, all the other conditions being the same, results obtained with the ISO methods are likely to be slightly higher than or equal than the results obtained using ASTM D4716. Now, if we look at performance testing, at the end, it's pretty much the same. The new ISO method reflects pretty much the ASTM D4716 method. I want to add something. There was, I think 2 weeks ago, the approval of a modification to the ASTM D4716, which allows to do thickness-driven tests, which is another thing which is going to be very interesting. We'll see after. So now let's enter long-term performance of the geocomposite. So again, what I'm going to focus on now is the reduction factor for creep, chemical clogging, biological clogging, geotextile intrusion, and laboratory. Creep is for creep deformation, chemical clogging, that's what I just said. First thing first, what are we talking about in terms of reduction factor? If we look at the recommendations which are published in the ISO 18228-4, which is in press right now, you have these indicative ranges that you can see on the screen right now. So it goes from 1 to 2 for geotextile intrusion, 1 to 6 for creep, 1 to 1.5 for chemical clogging, 1 to 1.3 for biological clogging, and for laboratory we add another one which is 1 to 1.5. Overall, if you multiply all these reduction factor as requested by the method, you end up with a global reduction factor which can be anything between 1 and 35. So that's a lot. That's just to show the influence of these factors. I want to mention that the biggest reduction comes from creep with up to 6 as a reduction factor. So creep becomes a critical parameter to understand. So geotextile intrusion, the reduction factor for geotextile intrusion, so that's to account for the additional geotextile intrusions that will come after the test is being performed. So that's going to depend on the fabric, essentially. So when you have a woven geotextile used as a geotextile, the intrusion will be lower, and the reduction, the creep reduction of the intrusion reduction will be also typically lower than for a non-woven. You also have some products are sold on the market like cusp-plated sheets, which are used for building application. They typically use heat-bonded geotextiles. Heat-bonded have much lower geotextile intrusion in the beginning, just because they are stiffer. And on the long run, they also behave differently. So that's something interesting. Okay. And the other factor is biological clogging. So here you can see two photos, one which has been used by Kerner, which comes from, which has been, I think, taken by Kerner, George or Bob Kerner, I'm not sure. So it comes from a field observation. They observed this, the presence of roots as a major reduction of the flow capacity of the product. On the right-hand side, it's a testing evaluation. So actually, I've done this project many years ago. It's we had some leachate artificially circulated, pumped into the test equipment to monitor the change of flow on the long run. So the type of the biological clogging which can develop in a drainage geocomposite depends a lot on the environmental condition. You will obviously not have the same problems for roadways as what you have for landfills. So GRI GC8 and ISO 228-4 provide some guidance on the values of clogging reduction factor. What's interesting is that there is no test method available for determination of these values, so we really have to piggyback on the existing publication by GRI and ISO to select these numbers. And voilà. Some literature, including myself, questions the relevance of these numbers and the fact they are universal. We did some studies. So as I said, some years ago, we were on a landfill. We used the landfill arriving in the monitoring laboratory of the facility, and we pumped this leachate into some test cell, and we monitored the behavior. So this was published by Eigenzau and myself back in 2012 at EuroGeo in Valencia. So what we found is that in the condition we've used, we had some reduction factor that we could calculate that would be anywhere between 2.5 and 10, depending on the product. So if we had a geonet without any geotextile between two geomembranes, it would be obviously much less sensitive to biological clogging. If we had a geocomposite with geotextile and with a reduced flow volume in the beginning, obviously there was a higher propension for bacterial attachment onto a surface within the core, and that would lead to higher clogging, higher reduction. And different structure would behave differently as well. A biplanar would not behave the same as biplanar because of the turbulence, because of the geometry of the cavity at the end. So that's why we had lots of questions about the relevance of these numbers. However, I like to be the devil advocate, so I'm going to look at things the other way around as well. We also have to consider what are the actual needs when we define the biological reduction factor. When we design a landfill, which is the situation which is the most critical for biological clogging, when we design a landfill, we design the flow capacity considering the entire surface of the landfill exposed to rain, the highest rain occurrence. Let's assume that this rain is going to happen before, just at the end of the construction. Then the water accessing the drain, so the drainage geocomposites, will be 100%, whatever is this number. Then let's enter the operation. So at that time, it's still only clean water reaching the product. When we start to enter operation, we start to fill the landfill with waste. That means there is a layer of material which is likely to generate biological activity, thus clogging. But overall, it's also an absorption layer. So this layer of waste will retain some liquid that will never reach basically the drain unless it's raining, it's pouring rain for 2 weeks, which rarely happens. And so there is a fraction of this water, this rain, which is going to be absorbed, which is going to evaporate. And the more waste goes into the landfill, the less flow will actually access the drain. Eventually, after some time, we're going to install a geomembrane cover on top of these waste. So at that time, there won't be any more infiltration from the top. It's good. It's much less. Most of the liquid reaching the drainage layer is going to be coming from leaks, from side infiltration, if any, and different things. But at the end, some study made in France back in the early 2000s showed that the flow reaching the drainage geocomposite after closure of a landfill was about 500 times lower than it was right after construction. So that means we already have a safety factor, a reduction factor, a safety or reduction factor of 500, just because of the normal operation of the landfills. So to make long story short, for biological clogging, I think there is no one-fits-all answer. We need to define what we have, what are the conditions, and choose a reduction factor based on what's happening there. I want to mention as well that I tried to develop ASTM guide and test method as well in 2015 to determine a reduction factor for biological clogging. And that was a failed attempt. I will confess, it was not possible to find a consensus within the industry. So we really have to look at the actual condition of operation within a project to be able to assess in a way or another the reduction factor for clogging. Creep now, and I think I'm running pretty much out of time. So as I said, polymeric material will creep when exposed to a constant stress. So primary creep takes place at the very beginning when we install the load. Everything takes its place. The product starts to compress until it reaches its strength somehow. And that's what happens, we hope, before the first 100 hours of testing. Then after that, you have the secondary creep where the molecular change into the material takes place. So the molecules are reorganizing their place, and they are slowly changing position, which as an impact decreases the thickness, the cavity available for flow. Finally, when this arrangement reach a limit, which is not always the case, some products never reach tertiary creep, you can have a failure. That when the structure of the product is no longer capable of handling the load. Then you have tertiary creep, you have failure, which is what you don't want to see. So there's been many studies, but the one which is interesting and I elected to report is the one which was developed by BAM in Germany and which is reported in ISO 18224-4, which is coming this year. For this study, to assess what is going to be the residual thickness, residual flow, I'm sorry, for the drainage composite, it takes to know the creep deformation behavior of the product under the service load, the anticipated service load or a higher load. So we're going to have a curve correlating the thickness versus time for a given load. It takes to have a short-term compressive test and a short-term flow test, which is driven by what I'm going to explain. ISO 18228-4 also suggests typical lifetimes for determination of creep reduction factor. For temporary structure, it's 1 to 5 years, and for retaining wall tunnel, it's up to 100 years. And you see here, landfills are only 30 to 50 years. And I think these numbers make sense considering what I said before about the presence of a capping system and avoid overestimation of the needs there. So the technique which is recommended for creep, for determination of the long-term flow capacity, including creep reduction factor, is basically to take a test. So the creep test, the thickness dependent test. So you see for a given product, we have the time here, the thickness, that is a creep test for different loads. So sigma 1 which is the lightest load here. You see the thickness is higher and doesn't change as much. And the more you increase the load, the more you have initial deflection of the product, and the quicker it decreases in thickness. So you enter this curve, which is to be provided by the manufacturer, of course. You enter the time, the design time, and you see what is going to be the thickness, the expected thickness of the core at that time. Then you have a relation, which is so a short-term compression test, which is correlating the normal load with the thickness. So this short-term compression test allows to define what can be the pressure that we can use to perform a transmissivity test and obtain immediate flow capacity after deformation under a given load. So it's a thickness-driven test at the end of the day. So once we have defined this pressure, we can perform a flow capacity test under the pressure recommended and obtain a flow capacity. So that's a very interesting way to address, to determine the flow capacity after a very long term, based on a set of creep data, a short-term compressive test, and a flow capacity method. What I want to highlight is that the new ASTM D4716 is actually doing something even better. It skips this equation, this transition here. It goes directly from thickness to flow, in the sense that it allows to perform the test under a predefined thickness. So that's very interesting. It was approved, as I said, like 2 weeks ago. It's not in my presentation because it's very recent. And that may facilitate even this determination of long-term flow performance. How do we get to creep tests, to creep data? The archaic method, I will say, is the method where we load the product under constant load. So we have a weight, we load the product, and you can see here, we monitor thickness, or here, we monitor thickness under a given load for a very long time. These tests are extremely long. It takes, when we specify a 10,000 hours test, it's 1 year and 2 months. If we say, okay, let's go simple and limit ourselves to 1,000 hours, that's still 40 days. That's way too long. Practically, it's impossible to use this test and to test up to the end of the service life of a product. It's completely impossible. So to address that, the industry has developed the SIM test, accelerated creep test, which is an ASTM standard since many years, D7361. In this test method, we use temperature to accelerate creep. So there is a whole science which is behind that. I'm really running out of time, so I have to accelerate my rhythm. But basically, to make long story short, you can project within a 24 hours long test, a 1-day test, you can project duration over 100 years. And the really good thing is that you can do that for an actual service temperature, which is not the case for the basic creep test. With the SIM test, you can say, okay, the temperature of service is going to be 35 Celsius. So let's see what is going to be the residual thickness after 100 years and 35 Celsius. So you can play with these numbers. It's really extremely performant to assess very long-term properties of drainage geocomposites. So that's a typical result for a SIM test. You have the retained thickness, you have the creep modulus, and you can basically determine what is the thickness reduction after any duration. So you see here 100 years, you could theoretically go to 1,000 years, but it makes no sense after. So,
hey, Eric, you've got, it's about noon. You've got about 4 slides left. How can you wrap up in a minute or two?
Yes, exactly. I'm doing that. So creep reduction factor, example of creep reduction factor, which are published in the ISO method. It goes from basically, for a geomat, it goes from a little bit above 1 under low load and low lifetime, and it can go up to 6 for much harsher conditions. I think I will skip the influence of the tangent stress, which is another consideration, which is actually very important when you have a standard GeoNet. But if anybody's interested, you can call me. I can go there. Reduction factor again. So I've presented you what's in the ISO method. GeoMat will have a reduction factor of typically 1 to 6. Biplanar GeoNet can be typically 1.3. You see also the difference in duration and normal loads, by the way, and all the numbers are going to be affected by this consideration, and temperature. Triplanar is typically lower, 1.1, box type 1.1. Tubular drainage geocomposites, which I did not really discuss in detail today, typically the manufacturer claim they don't need to consider creep, and I've contributed to some papers stating that. So value of RFCR of 1 can be considered in many cases under specific conditions. So overall, the short-term flow capacity will depend on the structure and properties of the product, boundary condition, normal load, hydraulic gradient, and settling time. That's what I presented in the beginning of my presentation. And the long-term performance will depend on the short-term flow capacity, which is defined here, as well as creep, biological and chemical clogging, and other factors, geotechnical intrusion, and so on, which are typically included in there. What I've not covered in this presentation, and which is important in real-life design, viscosity of the liquid. When you have a liquid which is more viscous, it may affect the flow capacity. Dynamic and cyclic loading, not addressed at all. Polymer aging, I've seen very limited number of specifications requiring OIT and stress cracking of the polymer, but typically this is not really addressed for this product. Capillary breaks, which are another discussion, and any extreme projects. And finally, the other relevant design concern for drainage geocomposites, the geotextile and UV resistance. This is very often a primary source of failure. When the product is not covered immediately or very quickly, it's an issue. Filtration properties of the geotextile, and consideration related to the structure. So veneer stability, interface shear strength, gravel puncture, and so on. So, yeah, drainage geocomposite offer an excellent solution compared to gravel for all the reasons. And that's a discussion which is common to any geosynthetics. Consistency, performance, sustainability. Sustainability is a big hammer in favor of geosynthetics. Constructability, greenhouse gases emission, and very good scientific knowledge around the product. But at the end of the day, we should never forget that deficient drainage is typically a root cause in the failure of man-made structures. It's I think everybody listening to me today knows at least one situation where drainage was a cause of failure. There is a variety of products, and they all have different properties, and they must be assessed individually. You cannot take a set of results and transfer it to the next product. Impossible. So at the end, consult a specialist, which can be the manufacturer or a consultant, to make sure that when you perform a design, you have a cross-examination of critical factors. There are lots of people who are very competent out there, and you should really use them. So that's all for me. So I'm behind schedule by 5 minutes. I'm sorry about that, by a bit more than 5 minutes.
Thank you, Eric. Because we're a little over time, I want to tell everybody that we'll be conducting a follow-up podcast with Eric on Thursday, June 18th, this Thursday. So please send any additional questions via the webinar survey that you will be sent shortly after the webinar concludes. And Eric will address these additional questions in the podcast on Thursday. For those of you that have time, I'm going to try to run through a few questions. Eric, can you go to the next slide?
Yes.
This has contact information for Eric, myself, and Jen Miller if you want to send us questions directly. Eric, can you go to the next slide? Our next webinar is by Andrew Mills on packaging, handling, and storage of geosynthetics. That's Thursday, July 9th. at noon Central Time, and there'll be some announcements of that. Finally, the last slide gives you some information on the FGI website. All of the podcasts and webinars are available on the FGI website. You can go in, listen to a webinar, and if you complete the entire webinar, you will receive a PDH certificate for that, as well as some pond leakage calculator, cost calculators, photos, technical papers, etc. on the FGI website. So with those announcements, and we're over time, let's go down to some questions. If you need to leave, that's great. You can tune into our podcast, which will be recorded next Thursday. So Eric, I'm just going to pick out some of these questions. There has been an issue with clogging of the upper textile in a geocomposite. What is the solution, or how do we limit this issue?
Okay, that's an interesting question. I think the understanding how the clogging took place is very important. I was very happy to be elected to drive the development of ISO 18228-3, not 4, for filtration design. And so while gathering information and producing first drafts, at the end, we realized that installation is a key factor which may affect the performance of a geotextile filter. If the geotextile filter is covered immediately by soil, without any dust, rain, mud or slurry flowing onto the fabric, usually it's going to perform very well, per the design at least. If the geotextile is covered after some rain event, very often what's going to happen is that you're going to have the erosion of soils which are nearby, which is going to flow onto the product, and which tend to clog the fabric on the surface. So what I'm describing is specific to some configuration. Of course, it does not happen everywhere, but installation is a key factor. Second factor is to have obviously a proper design of the soil geotextile compatibility, and that would really have to be analyzed with respect to the specific condition of a project. But answer is in two directions. First, installation. How was the installation made? Second, it's not ranked by order of importance, by the way. Second, the design of the soil geotextile compatibility.
Okay, thank you, Eric. Next is, how do you feel about the use of ATV vehicles, you know, the four-wheel ATV vehicles, to traverse or cross over deployed geocomposites and geotextiles?
Oh. That was a tricky one. I don't have a fixed opinion on that. I need to understand better the situation and the configuration. I cannot answer that question.
Okay.
I'm sorry.
Next is, what is your recommendation for testing a geocomposite? Test the individual layers or test the sandwich of the layers? So I guess if it was, say, a leak detection zone, put the GCL primary geomembrane above it and a compacted soil underneath of it. How would you handle the testing?
Okay, if I understand well, how to test in the lab for transmissivity geocomposite to obtain a representative flow value. Is this correct?
Yes.
I would definitely recommend to use something as close as possible to what is used on site. So, and to stop reproduction of this system where it has no longer any influence. So in that case, if you have a GCL, geomembrane, geocomposite, and soil, or another geomembrane on top, I would recommend to use exactly this structure. So GCL, geomembrane, that means you need to wrap everything to avoid leakage through the GCL, of course. But make sure that the boundary condition reflects what's going to be on site. What is very often done is to have only the geomembrane installed because it's much easier. And to put the geocomposite on top and the soil on top, that's definitely one solution that is very commonly done. But if it's under very high load and there is some concern that the geomembrane could deform into the composite, which is not really a good design, then probably it's better to include the GCL into the structure.
Yep. Next, is the non-woven spun bonded geotextile suitable for use as the outer filter fabric or upper filter fabric of a drainage composite, or what would you recommend?
I think depends on the manufacturing technology. For cusp-plated sheets, which are used in the building industry, it's probably, I think it's always heat-bonded fabrics, which are installed on the core. The reason for that is that in the manufacturing process, it's easy to apply the fabric immediately after extrusion of the dimpled sheets. So the adhesion between the fabric and the core is immediate and is not questionable. It's very good adhesion. When it's a GeoNet geocomposite which is manufactured, the process which allows to laminate together the core and the geotextile is a second process. So first, the core is extruded. Second, the fabric is heat bonded typically to the core. So that means there is a reheating of the core and you apply the fabric on the reheated core. So this secondary process is the source of many discussions. The regularity of the process is not ideal. There is an excellent paper by Rick Thiel, which was published last year on this, where he proposed some quality control strategy to address this. So at the end of the day, a heat-bonded fabric, the problem is that the adhesion in this secondary process, reaching a good adhesion between the heat-bonded fabric and the polyethylene core, which is typically polyethylene, is extremely difficult. The chances to burn the fabric, to have no adhesion, are very high with the technique which are used nowadays. If it were a different welding mechanism between the fabric and the core than heat, maybe that would open some perspectives, and then it would be really super interesting. You know, I would love to see a heat-bonded fabric on top of a GeoNet. That's what's going to give the best flow capacity.
Yep.
But right now, it's really manufacturing which is a limiting factor for this application.
Yep. Here's another question, sort of after one of my areas of interest. Why is elevated temperatures in a landfill not considered as a reduction factor like biological clogging, creep, and the other reduction factors you covered?
I don't know if this question was requested before I speak of creep, but with the SIM technique, you can actually include temperature in the discussion. You have to look at how the temperature will affect the different reduction mechanisms. So for biological clogging, the values that we're using now are anyway tabulated. They are not experimental. I'm not aware, except for the study I've done, I'm not aware of strong studies on biological clogging. So it's really tabulated based on experience, based on consensus by the Geosynthetic Institute. Is definitely the organization which has proposed the values which are commonly used nowadays. And to my understanding, they consider temperature. For creep, using the accelerated creep test, the SIM method, D7361, offers an opportunity to consider the effect of temperature in the creep thickness reduction of the geocomposite. So temperature can be addressed easily. It's a calculation. It's a test. You need to have the data, but it can be considered.
Okay. This is a design question. It's somewhat lengthy, but I think kind of timely with at least some projects I'm involved with. Do you have any thoughts on how to design a very shallow and long slope? There are a lot of impoundments with 2% grades and a slope of 1,000 feet plus 300 meters. It is almost impossible to design such a closure to not have a flow depth of greater than the thickness of the geocomposite. Is there a more practical consideration? And some thoughts come to mind. Maybe you stack 2 composites or 3 composites to give enough capacity, but go ahead, Eric.
Yeah, I think when you have such a long slope, what I've seen in other design is to have intermediate trenches. So after don't forget also that the rolls have a length. A roll of geocomposite has a finite length, let's say 100 meters. I don't know, you have to check with the specific manufacturers. But having playing with this length and making sure that you have a trench collector halfway, collecting this liquid from the first part of the slope and then directing that further down through a parallel system, through a pipe. That cuts the 1,000 feet length slope is going to be cut in several pieces. It can be 3 of, let's say 4 times 250 feet. And that makes the design much more realistic and much more stable, because if you have a failure taking place, let's say you've made a mistake. Instead of cutting at 250 feet, you should have cut at 200 feet. And you have a failure on the last 50 feet. At least you don't have 1,000 feet of slope going down. It's a safe and easy way to handle the problem, I think.
Okay. Does the ISO method of testing cover the determination of discharge capacity of the geocomposite, like a prefabricated vertical drain, in a kink condition? In other words, if the composite gets kinked in the field, should you consider that in the testing?
Okay, for prefabricated vertical drain, there is an ISO test method, which is ISO 18325, 18325, which is specifically designed to address the testing issues. There is a similar ASTM standard. I think it's 6918. I don't know all my ASTM by heart, I'm sorry, nor ISO. But it provides very specific guidance. The ISO was published like 5 or 6 years ago. It provides very specific guidance on how to address the kink condition. And that is not covered at all in my presentation. For prefabricated, I would be very happy to have a discussion outside of this conversation, because it's very different fish, very different objectives, very different consequence of failure, in the sense that if you have a lower capacity, flow capacity on the PVD, it's not affecting the stability of a structure as much as may a geocomposite like what we're discussing today. So that's a discussion I would prefer to have outside of this discussion, the one we have now.
Okay. We have many more questions, and we'll get to them in the podcast. Maybe I'll wrap up, Eric, with one more. You sort of touched on it in your presentation. What about the flow in the transverse direction in a large landfill cell? This is an important consideration for leachate collection, and you talked about flow parallel to rails and transverse or perpendicular to the rails. So how would you handle that in a large landfill cell?
Okay, first thing, for having some data on what is the actual capacity of a product in a lengthwise and transverse direction would be the very beginning. If the size and the shape of the project justifies this kind of consideration, it will justify investing the $200 for a test or whatever is the amount. So it would take, by gathering data on transverse flow versus longitudinal flow, and from there adding that as an extra reduction factor, which can be design related. The guidance that we have, which are published by ISO or ASTM, they do not preclude to add more reduction factor. So you can, that's it's a standard, it's a consensual document. It provides the minimum that you must have to make sure that the system is working. From there, you can add more reduction factor. It's designed by the engineer depending on the particular project. So that's how I would do it. Gather some data, and if there is a risk to have a misalignment of a geocomposite to the slope, take it in consideration by increasing the flow capacity requested or specifying transverse direction flow.
Great. Thank you, everybody, for attending. We will address the remaining questions in our podcast on Thursday. If you have additional questions, please send them to me or Jen Miller, or add them to the survey that will come out after the webinar. Eric, thank you so much for an excellent webinar, and the list of questions is very impressive, so you've generated quite a bit of discussion.
Excellent.
Thank you for that, and thank you for joining us from Montreal, Quebec. And everyone, thanks for attending, and we will see you next month for Andrew Mills' webinar. Thanks for being here.
Thank you.
See ya.